Good afternoon, colleagues, ladies and gentlemen. Welcome to this pair distinguished lecture series. My name is Qing Chen, the director of the Purdue Academy for Interdisciplinary Research, or PAIR. Today, I'm very happy to introduce our distinguished speaker, Professor ZHANG, Chair Professor at the University of Science and Technology in China. Professor Zhang is a world leader in exploration geophysics, AI-driven seismology, and interdisciplinary sensing technology. His innovations spans a remarkable spectrum from seismic imaging for oil and gas exploration to real-time earthquake monitoring and transformative medical imaging. His career is a testament of a blend of science excellence, visionary innovation, and entrepreneurship, underscored by more than 220 publications, 40 patents, and several high-tech companies founded. Professor Zhang is among the first to develop groundbreaking technologies and concepts, including tomographic imaging. He brings a CT scan-like technology underground, allowing oil and gas companies to see Earth's layers more clearly and locate oil and gas resources with greater accuracy. AI-powered earthquake monitoring. He created the world's first national earthquake monitoring system powered by AI, enabling faster and smarter detection and response. During lunch, I just learned that he actually predicted 2 of the earthquakes among the 5 recently happened in China. And actually, the prediction is a few hours earlier, not just a few seconds. Normally, for earthquake, if you could predict just 5 or 10 seconds earlier, you can really save a lot of lives. So this is remarkable. And then the intelligent listening. Professor Zhang leveraged advanced sensors to AI to listen to cities. This concept of intelligent listening is crucial for real-time monitoring of infrastructure health. So beyond the geophysics, his work extended to biomedicine, leading startups that develop new cancer and viral therapies, including efforts against the coronavirus. So Professor Zhang's distinguished contributions have earned him the highest honor from the Society of Exploration Geophysics, election to the U.S. National Academy of Engineering, and the recognition of as the first in Fast Company's list of 100 most creative persons in China. So without further ado, please join me in welcoming our distinguished speaker, Professor ZHANG.
All right, thank you, Professor Chen and Professor Chen Jinyan and Professor Chen Jianli for inviting me to be here. It's a great honor to meet with everyone. Okay, so I will talk about the machine listening, extending AI from vision to sound and vibration sensing. And before that, I want to share with everyone my career path, how I come to this point, developing, studying, sensing sound and vibration. I've been 38 years ago, I went to US, benefit tremendously from US education. And after graduation, I was teaching, I was doing company, teaching at MIT, Stanford Geophysics. I came back China, I formed my own research group at USTC. One of the requirements for student, every student must be able to run marathon. So we finished over 30 marathons, our group, over last 12 years. And recent years, I brought back a team from US, landing in Shenzhen. We're studying machine listening. I will talk more about that. As we know, biomedical science launched really about 10, 15 years ago. At that time, I thought it wasn't too late, so I could catch that moment and then study the biomedical science. So I invested in that field and then formed two teams. I served as a CEO of the companies. I lead a research team to develop cancer vaccine, which I will briefly talk about. Since I was teaching at Stanford, MIT, then when I returned to USDC, one of the platform I established to bring students from 3 universities together every summer, and then faculty every summer, and then president of 3 universities to meet until we stopped, exchange with the US. Briefly introduce the challenges research have been involved in during last around 30 years as a professional scientist. So major challenges in science technology. First, I went to US, went to Penn State, received a master's degree, and MIT for PhD with the two distinguished professors in the field. And then it ends up 28 years, I was doing that, developing that for industry and also involved teaching in academia. I founded a company called Geotomo in 1998. And after 15 years, I returned back to MIT teaching geophysics. And the company keeps growing and operating in over 60 countries now. And been 28 years. So during those time, very fortunate, I met a number of pioneers in geophysics in the US, 3 other legends, Ozzy Yilmaz, Mark Zuckerberg, Lee Bell. They all graduated from Stanford. They were students in 70s, in 80s. These 3 guys and basically established a foundation for oil and gas exploration. So because of their early contribution and the whole world, over 6,000 companies emerged. So they are the pioneers in oil and gas exploration. I caught the moment in 1998, begin from there. I collaborated with them, founded the company, and then later we start different business efforts. 25 years ago, I began to get involved in medical imaging. Yeah, we know the fundamental physics, similar, yeah, Earth imaging, medical imaging. So in 1998, we founded a company to do digital X-ray. At that time, everything becomes digital in the medical field. We began to see DR, CR, transforming from film to digital data in medical field. So since we were in oil and gas, we know how to process data, and then we began to work on medical device. And one of the devices very popular in China called matrix scan for bone density testing. Been in China almost most health examination center. And as I mentioned, 10 years ago, biomedical emerging. So it leaves opportunity for everyone, even those who haven't had education in biology or medical, begin to learn to what it's about and do things. So I began to do the animal studies, which I hate when I was a college student. I don't want to touch chemical, don't want to touch biology, but I found it a lot of fun. So working with my team, developing nanoparticles for drug delivery. One of the efforts to try to solve the infection problem using human cell to develop a small nanoparticle as a faked cell to absorb the toxin, and it's already in clinical stage. And then at the same time, we form another team doing cancer vaccines. In the world, until now, there are 5 companies competing for developing cancer vaccine. We know, COVID vaccine, so on, right? For healthy people. Cancer vaccines are not for healthy people, for patients. So treating the cancers, making sure cancers disappear, and then no longer return. So once you trigger the immune system to activate, then it will fight with the cancer cells itself. In that sense, it's a vaccine, but for cancer patient. So I lead a team now in China, and we're in clinical study. We're doing that in Beijing. The 8th patient is treated, so far has been treated. And we have 75% patient have reaction, and they stopped growing cancer. And right now we're still in the middle of that experiment. So very exciting effort. The recent 3 years, I came back to China and then began developing machine listening, earthquake forecasting, as Professor Chen just mentioned, listening, and develop a digital, digital transportation, using the sound vibration signal. And the team come from US, about 20 people around with the US education background or working background. I will elaborate a little bit further, talk about focusing earthquake from what we listen and so on, using AI. So, well, 38 years, student and scientist, professional, faculty member, so on. I have a lot of reflections in my life, long enough. So I initially, when I was in college, I hated most is geophysics. It's very boring, I feel. In the classroom, teachers talk about equations, the Earth's magnetics, which I feel nothing to do with me. But years effort in the US, I began to realize I didn't know what I loved by nature, only by fully committing myself. Only by committing myself, and then giving everything I had. Then I began to realize, wow, so fascinating. So I got involved in 4 different fields. That's how I got in there. There are many smart people in the world. I found, I happened to study in a few distinguished universities, just like our PolyU, and met many smart people. But I found you have to keep learning. You learned from school, from college, and then you try to settle your life. It's just not that easy. You have to keep learning, constantly broadening your horizons. And the other lesson I learned, I found a teamwork. You got to have a team. You can't do it all by yourself. Today's science and technology, the development requires teamwork, and you have to be able to manage a team all the time. So now let's come back to the topics, machine listening. Why we do that? First principle of the physical world. All mechanical motion, structure change, and energy exchange inevitably generate and propagate sound and vibration signals. If we look at today's AI world, Li Feifei, a professor at Stanford, she established a company called World Labs with 30 people. They have a team developing large world models, 3D spatial intelligence. Of course, we heard OpenAI, developing large language models and many other things. Anthropic is another large AI company releasing cloud models for reasoning, for programming, many things. So in the AI world, it's quite busy. A revolution is occurring every day. But we have to realize everything is in a silent world, which is not real, not true. Actually, in terms of humans' 5 senses, we have vision, hearing, touch, taste, and smell. Between 10 to 15 years old, we began to develop capability close to adult level. People keep asking me, what about robots right now? How old, what age is like in human? I found the vision is pretty mature right now, but hearing only half us. Speech, conversation, that's fine, but physical word sensing is not there. And touch, taste, smell is even further behind. So maturity level is still low in today's robots. The reality is currently autonomous driving systems are deaf and not able to sense what happens in the surrounding environments in terms of sound. Robots still cannot interpret sound environment. Yeah, only can talk with the help of a larger model, a conversation, that's fine. Critical information on the city surface is difficult to capture, and changes in the underground urban environment remain invisible. And in terms of human visual auditory perception, in China, the public cameras, first level city, it varies from 250,000 to 1.2 million cameras, a lot of cameras, but the data remains largely underutilized. The sound data, right? Only use images. In terms of consumption, human consume 65% on the vision, 35% on the auditory energy, on the listening, and in terms of digital data, video data volume per hour about 1 gigabyte, audio data 1/3 of that, vibration data much smaller. But the bottom two, audio and vibration, we're not using in our world mostly. So that's why we from this team developing machine listening for recording and interpreting both sound in air and fluid. The sound propagates in air and fluid only. Once go into the earth, it become vibration, elastic wave, vibration propagating in the solid medium. So just recording is not enough. Listening is not enough. We need to interpret, right? We need to interpret what we record. So we move from machine listening to intelligent listening. Intelligent listening just enables machine to perceive, understand, interpret sound and vibrations, turning them into actionable information. Of course, it should do a lot. Detect events, whatever happens, vehicles, failures, impacts, identify anomalies here and there, monitor structures, track traffic, sense subsurface changes, provide early warning for natural hazard. So who should work on intelligence and listening? A field which has been missed by the AI world. We found that it has to be developed by an interdisciplinary teams, combining people from geophysics, acoustics, AI, sensing hardware, and urban engineering. So if we look at the landscape in terms technology, in terms intelligent vision and listening, AI vision is very mature. A lot of companies in there, AI speech, a lot of companies in there, but AI sound, vibrations, not much effort, just emerging in recent 3 years. So 3 years ago, we founded two entity business companies, Bafang in Shenzhen, Hefei in China, in US, Silicon Valley and Houston Life Science. So two different companies are doing their machine listening, and at the same time, almost same time, several companies in Korea, Japan, Switzerland emerged because of the need of robots sensing for surrounding environment. So several companies coming up. If we look at the physics, and we have the air, and it's really the sound wave propagates in air and fluid. That's the sound wave. And between 20 hertz, 20,000 hertz, human can hear that. But above that, ultrasound, we can't hear that. Below, we can't hear that. The inaudible infrasound wave really propagate very far, carry a lot of information, but we rely on machine to record. We can't hear that human. Once get into subsurface, get into the solid medium, becomes elastic wave, and then you can't hear it. So we rely on sensors. And scientists use sensors, recording elastic wave and performing research, conducting analysis to find the Earth's whole Earth structure and Moon's interior as well. So the physics, this AI different from all previous image-based AI problem, which mostly rely on data. We're relying on data and the physics. What's the physics here? If you create an impact at the surface, it generates acoustic wave propagated in the air, recorded by a sensor. And then it will get into the Earth, get into the subsurface, and propagate as an elastic wave in the form P wave, very fast, S wave, and then surface wave. So what is a P wave? P wave is a wave propagate, vibrate along the propagation direction. It's very fast. S wave vibrate vertical and then moving forward along the direction. So slower. And then we have a surface wave called a lava wave or relay wave, depends on the particle motion. It could go like horizontal, the lava wave, or vertical, relay wave, which carries the most energy from an earthquake. You produce any source, you produce any impact, like vehicle, like you walk on the ground, you actually have all of those waves. From those waves, you can backward to infer the source type. Is a human walking or vehicle driving, or is it an earthquake? You can also infer the media, what change the propagating media. Is there a collapse? Is there a cave? So on. So that's what geophysics does. And today we're trying to elevate that technology into real time, so become a listening type reaction. Exploration seismology. We have been interpreting seismic waves, seismic echoes from the subsurface. And what we did in the marine case, we shoot air gun, and then the wave get into sound wave, got into subsurface, become elastic, and then echoes. We interpret that the subsurface structure. On land, we use a truck to strike the surface. And the signal like this, every shot, every gather, has a lot of vibration from the subsurface. From there, we can process our data to see the detailed subsurface image from surface down to 10 kilometers, which becomes the base for oil and gas drilling, right? We know exactly where to go. And this is geophysics. But that type of effort takes typical from 9 months to a year. It's a long effort in oil and gas. We can use that for real time, listening. So we have to advance that with more efforts. So the challenge, real time. The challenge, real time. We have the noise data. We want to denoise in real time. We have a node sensor, very, very small, getting cheaper over time. We detect signal even below the noise level. We got to locate where the signal comes from and the size, the nature, the attributes, so on, right? A lot of things. So we have been doing that, publishing paper last 10 years. So coming to an AI stage, we combine the geophysics with the AI together to train a robot. What happens? Simulating human, how human learn from listening. Human has to watch something, right? Hear at the same time. So we combine sound, ground vibration data with the video data to train the robots. After training, the robot turn back, and now he or she hear a kid running behind. Then a robot can guess, oh, this boy, 8 years old, 50 meters away from me at whatever speed, right? So this is how I learn. This is an experiment my student did. Along the road, we put a sensor sensing the sound. This is a vibration signal. Try to correlate to learn from this image. Establish an imagination cartoon. Which line? Which traffic line? What speed? What's the size of the vehicle? Training. Right. So after then you can turn off. You can turn off this, turn off the camera. And only by sound and vibration, we can guess which line the vehicle. Equivalent to someone sitting along the road back to the traffic, guessing what's happening. So this is one of the example, simple example of intelligent listening. Okay, and so today, after 3 years effort, we've been established this configuration. We put sensors everywhere, on dam, on slope, on bridge, on highway, building. We use 4G to transfer data real time. About 5 to 10 milliseconds, one small data set to the server. Using AI to calculate less than 1 second, and then 5 to 10 milliseconds, push the results to the terminal so that the terminal clients can access the results in real time. If necessary, then we use a video camera or turn on, right? Just like human, heard anomaly, then we look and see, right? If necessary, then further we will send drones to the site, inspect any anomaly. So this intelligence system have been well established in China, running in many provinces now, and also in the US right now, and plus Holland, Shell, and oil gas companies using that as well. And in Hefei, it's a project called 全域成安. I don't know, in English we call it city size. Huh? We call the first time I talk about city size. We call it 全域成安in Chinese. So in the city, we install 50,000 seismic sensors from 10 different applications. Monitoring extreme weather impacts, earthquake, landslides, subsurface structural changes, high-risk building safety, urban digital traffic, subway operational safety, real-time security monitoring, which means you have a, if intrusion, so on, certain facility forbidding people coming close, right? Large event risk management, like sport event, music event, comprehensive noise surveillance. Once data are digital, you can tell a whole day around, right? What's the noise like? And also drones, low altitude flight monitoring for drones. I will show the examples, a few those. So as I mentioned, the idea to be able to see and listen together, that's how humans learn in the real world. Now we're training our system doing the same. So for example, if you have an event, have a car accident, have people screaming, running from the video camera, you catch that data and process, immediately trigger the nearby cameras, right? So you don't have to run your camera, 250,000 cameras, don't know which one to use. And this is what happens, like after raining, the red zone, it shows the water concentrating zone. So using our sensor, we're able to tell the surface wave velocity variation. When you have water, flooding on the surface, the shear wave velocities have been tremendously reduced. So you're able to image where the water goes every 10 minutes. And every building has several frequencies vibrating. You want to monitor if they are out of the standard range. This is traffic, okay? 3D digital traffic with a capability viewing. With a capability, you have a camera, you have a listening, you have a sensor, sound vibration sensor. You're able to do a lot more. Above road, tracking the traffic flow, creating a digital, transportation. On the road, we can understand the contact variation between road and tires. Below road, we can monitor structural variations and potential sinkholes, so on. So all using the same set of system. So once it become digital, the digital, you have each, this is the, you see the curve, each data, sound vibration data for each vehicle, and we can track them. So we can digitize and know where they are, the speed, the weight, When we have a car accident, we don't need to wait phone call. We see on the screen right away. We see the flat tire, and it's like a big bomb to our system. Report traffic jams and also falling object from vehicles. We can tell the specs. So not only that, when we are able to listen to using machine listening, automatic along the road, and this is along the road sensor. Horizontal, every little number is a day. See, this is in Hefei. It begins raining and then begins snoring and then freezing. So you know exactly when the freezing, when the surface condition begin to change rapidly. So this is based on the sound entire, the sound data. So we can infer the vertical horizontal stress change. This is entirely based on physics rather than just using camera. On the other hand, on the surface, the moving vehicle serving as a random source. So the elastic will propagate in the subsurface. After raining, we can tell where the water stored in the subsurface. Down 10, 20, we can image even down to 100 meter in depth. So real-time monitoring the surface and subsurface. And this is a real situation in Hefei. We can tell there's along the road, every 100 meter we have a sensor, sound vibration sensor. And then we have camera, probably 5 kilometer camera, right? We don't have a lot. Very expensive. So one vehicle, we track the vehicle from their sound. When it pass by its camera, then we catch that. We assign the plate number. The whole vehicle behavior on the road will be tracked. So we have millions, vehicle information, driving information. And not only the driving pattern, also the surface, as I mentioned, the surface slipperiness and subsurface variation every 10 minutes. Authority using this window to monitor anomaly like overspeed, overweight. By the way, from the wave propagation from this vibration signal, we can estimate the vehicle weight. I will elaborate a little bit more further. My student, our colleagues, did a tremendous, remarkable work. So for measuring, estimating vehicles' weight on the road, there's a weight in motion device right now worldwide has been used. But this costs $1 million or $1 million. You need to break the road and install the device. 7 days, and then you can resume the traffic. In our case, we use 2 seismic sensors, really, and then 2 cameras. One catch the plane number, the other one to catch the side axle. But right now, we're using 1 camera only, reduced to 1 camera. And then we do a lot of AI training. Train the seismic data generating from vehicle. And then the camera, we can use a large model. And today we're dropping that because we're learning from our own model. After that, you can estimate the weight, and your camera catch the color. If it's overweight, then you can issue warning. So what happens? This technology, using sound, using machine listening technology, we dropped the cost for estimating vehicle on the road from $1 million to from 1 million yuan RMB actually to 20,000 yuan. So it's a tremendous drop. And testing by authority in Shenzhen, they tested 2,000 freight vehicles, which are heavier than 10 tons. The red curve is their true index, one by one, from the lower weight to higher weight. And then the testing result, we found that we can make 90% of accuracy right now. That's enough for a lot of applications. So it's not a magic, really, following Newton's second law. The wave generated associated with the weight of the vehicle and the axial configuration. So you have the displacement, the acceleration, and then you have a force impact. The force impact is associated with the velocity, the speed of the vehicle, and also the weight of vehicle. By using deep learning, you can reveal the relationship, right? Instead of solving the wave equation. It helps. It helps really solving the problem. So a real operating system, this is like commercial one, operating in different many cities in China right now, and in 3 provinces now. But in the fall, there will be over 1,000 locations. They will be using that. And monitoring buildings, listening to the building. We have a sensor installed on the top and the bottom, listening the sound and vibration of the building. Okay, so we can monitor the building between 2 sensors, the building, also listening to the ground nearby, 1 to 2 kilometer zone, below what's happening. And this is the case in Shenzhen. We found a fracture appeared on the surface of the building. One of the vibration frequency we monitored, this is resonant natural frequency of the building. Dancing, can no longer recover. It just going away crazy and then crazy. It just it's not behave normal because the building fractures. Another case, this is a building we're monitoring. We monitor a lot of buildings. Right now we're setting up a monitoring for 2,000 buildings in Shanghai. And in Shenzhen, this is a case like construction nearby the building is okay until this October 23 last year. Suddenly we found the building, the basement, there's a collapse. And the structure can no longer recover, and the vibration frequency keeps dropping. And so in the end, the government issued a warning to the nearby neighborhood and also to the construction company. So this type of service, as I mentioned, over 3-year development. This is one of the efforts I showed that has been in real application right now. Construction is an issue in Shenzhen, in many other cities as well. We have the TBM operation drilling the subway tunnel, right? And this thing can cause a lot of trouble because during the process, we'll spray water, hold the nearby structure, from collapsing. Here is this example, the water will go up to the surface. So you want to stop that in real time and then seal it with the cements. After the whole thing, sealed, then you can continue to go. Otherwise, in Shenzhen, we learned there are few very famous incidents. Also, we see this is another construction last May. Just suddenly we found in a specific location what happened, the pipelines were broken because the TBM operation, 盾构机, 中文就是盾构机, TBM. So causing the water saturate, causing low velocity, velocity reduction in the subsurface. We got to stop that. Another example we know is 2024 collapse in Shenzhen, and they began to inject cements, but it goes forever. They don't know where it went to. So on the surface, we monitor what happens subsurface. This is the injection site. Nearby still collapse. And then the second day, it keep feeding, and the third day frozen. So we know, oh, now you're fine. You can resume. So we have now the commercial package going along with the subway construction. And also we can monitor dams, right, embankment. And this is an example in Hefei during the high raining season. So they concern so much, they put 10,000 local people to inspect just in person manually. We install our system. And then one day on 2024, July 11, in the morning, 5:26, issued a warning that there's a leak of the water causing the structural change, subsurface. You can't tell from the surface. You can't tell anything, but inside, creating a leaking zone. So 7 a.m., the city mayor called me, asked what's going on, how large the damage could be. So we explained, and then 8 o'clock, the rescue team began construction to fix that issue. So it's a well-known case. Slope infrastructure, continuous slope. Slope is a major concern in China because we build highway, railway, everything in a rush. We have like Zhejiang alone have 20,000 slopes, which may have the risk of sliding. So we install sensor doing the 3D image of the bedrock, what's like, where it could store the water, and we monitor that. There are rock type slope, there are clay type slope, and we monitor the inside resonance frequency, the material density changes, so on. So during the storm, you can see the velocity, the resonance frequency suddenly drop. It recovered later. If not, continue to slide, then we issue warning. Here we see the water saturation. Blue means because of water saturation in there causing velocity reduction. You want to make sure it can be recovered. If not, we issue warning. On bridge, we do the same thing. We monitor we listen to the vibration of the bridge. The bridge very sensitive to temperature. This is the daily temperature. Every day, the high and low. At the night, the low temperature. At the same time, you just see the bridge is like a noodle. It just becomes soft during the day, increase the density at the night, and lower the density during the day when the temperature. Very sensitive when you monitor that vibration because of the traffic, their vehicles sending the elastic wave propagate in the bridge. So you're able to monitor the variations in real time. Okay, there are a lot of applications I mentioned in the city. We did meet the airport. This is the Baiyun Airport in Guangzhou. So we install sensor along the runway, listen the sound vibration. This is the landing of airplane, taking off airplane. But that certainly is fun to monitor their impact. But the more effort, actually, we use that signal to monitor the runway changes, subsurface changes. So on the side, it shows the velocity structure underneath runway every 5 minutes variation. So that when it has a damage or it's emerged as a water saturation, then we know what to do. And Shenzhen, Bao'an Airport, we monitored, the crowd, the people, population, where it is inside terminal, the low frequency. So when you have 200,000 people inside the terminal, like Spring Festival, major holidays, the authority need to know where are the people, right? Is they here or here? They certainly have hundreds cameras, but hard to estimate from cameras, and the low frequency vibration tell. We detect drones using sound vibration. So people keep asking me how you monitor that. The theory is such. It's when you have a drone flying in the air, it pushes a pressure, the acoustic wave pushing the ground. And getting into the ground, it becomes a source point on the surface, and then propagate along all directions. So our sensor pick up the elastic wave. At the same time, we have direct acoustic, receiving from the drone. But acoustic wave drops very quickly along the path, as distance increases. Elastic wave very strong. So this is an example. The elastic wave right here, you monitor the ground vibration, but the acoustic signal directly coming is behind, very weak, very weak. If you set up a array, you can tell where it is, the drone, so on. Our interest is to monitor drones below 300 meter elevation, 300 meter height, where radar missed, couldn't detect easily. And also, this is from the sound vibration signal, single sensor, you can tell so-called Doppler effect. From that curve, frequency response, we can infer the speed, the height, so on. So final example, my time is running out, coming here. Final example about real-time earthquake forecasting. It is a very challenging job in seismology. Seismology don't want to talk about that because it's hard, right? You could make a mistake. And US, basically, they conclude we're not able to predict. But who knows, right? Technology has been advancing because of AI. Scientists discovered the protein structure, found a lot of things, right, in science. So we give a try. What we found interesting in Hefei, 2-year period, over 2-year period, suddenly one zone is very active seismic. We found before 7 hours before, we use a very high density sensor on the ground to monitor the subsurface sound vibration. We found just 4 hours earlier, we found a sound coming from the crust, from the epicenter area. And then 3 hours, and then 1 hour, and then earthquake suddenly occurred. We'll have a very broad frequency response. Not only at the central point, you see the nearby, a lot of ringing effect. This is the earthquake happened. Afterwards, and all disappeared back to normal. From the rock physics experiment, we could use the result to explain when the stress increases, it could push the plate, rocks, could squeeze the rock and creating millions, of nano-size fractures. Just like creating a lot of noise instead of one single earthquake, and then stopped, right? And then you have a major earthquake, right? Because the stress accumulation, so on. So this is an interesting, subject. We're doing that. We don't publish. We're secretly working on that. 26 scientists working on this project. We hope, it could solve that problem for human, right? This is one of the tasks remaining scientists need to conquer. So I mentioned last 3 years, we have been doing a lot of things based on the concept of machine listening above, on, and below the surface. In the past, in geophysics, we use a sensor to monitor the subsurface only. But now we not only monitor subsurface, we monitor everything on the surface and also in the air. So we redefine the near surface to 1,000 meter above surface and 1,000 meter below the surface. This is our new, the zone. And our team in university and also in business sectors work together to try to solve this problem. We found it's very hard. It's an engineering problem. Very hard for university professor, student work on that alone. We need big muscles. We need big muscles from industry to help to solve the problem. So that's why we have multiple teams doing that. So with that, I conclude my talk, and I'd like to hear your questions. Thank you.
Okay, thank you all. Even though I have known Professor Zhang for 45 years, we went to college at the same time. We were classmates. But still today is the first time I got the opportunity to learn so much of his work. It's so special, inspiring. So now we have 30 minutes for questions. So we already collect some, questions, from other sources. We want to start from the audience here. Okay, you have a microphone.
Thank you, Professor Zhang. Thanks for this impressive talk. So my research is about seismic tomography. So I do have one question about in these slides. It's about something like a real-time seismic profile. So because to my knowledge, if we want to do some profile, we use first we need to do some forward simulation and use some iteration method to update the velocity model or S-waves model. So I'm quite curious about this. So why it works, and yeah, this is my question.
Good, very good question. Are you geophysicist?
Yeah.
Okay,
I do computational mathematics, but with the application in geoscience.
very good. Yeah, you see, in typical geophysics, in earthquake study or exploration seismology, we try to establish a true Earth model, right? We have been thinking of that for years. We can now bring that into cities because you can't do that in 9 months or a year to process data, which will limit our extension, right? So we monitor the changes. So we install permanent sensor. We don't know how complex the Earth is, but once it changes, we found it. That's the major, application demand in the city, right? So collapse or pipeline broke and so on, and you suddenly realize it's change, building collapse, building fractures. So monitoring the changes, you can do that within second. Yeah, it's a very good question. Yeah.
Oh, okay, thank you. So other questions? Yeah, in the middle. Oh, Qing. Oh, I'm sorry, Changwen.
Oh.
No, Changwen, you.
Okay, I think it's very amazing. You cross multiple fields, and which I think in many for us or some of the students here, we cannot imagine how that been done, but you did it so well. I have of course my electrical engineering or computer engineering background, so I think I had a question on the sensing sensors. How do you place those, especially on the city scale here? And I think in order to capture those changes, of course, you need to have some we call sampling density. How dense is going to be the sensors, especially in the city area? You have so much limitations.
Right. As I mentioned, like city like Hefei will have 260,000 cameras. We're trying to install 50,000 sensors. That's not much, right? Comparing with the camera. So along the highway, along the traffic road, we install sensor every 100 meter, one sensor. Within the community, it's different. If we monitor subway construction, we typically use a 30-meter spacing to understand where it happens. Or in certain construction project, we use a coarse sensor, maybe 10, a dozen sensors, but when we find anomaly, we'll increase sensor to locate where it is. So it's project dependent, but the demand is high. The sensor is much cheaper than cameras right now, right?
Correct.
So we could potentially create a market, really huge and contribute tremendously to the city.
Okay, I guess my understanding is you're doing this task dependent with the sampling density depending on the demand on the accuracy of the monitoring, I guess, right? Okay, thank you very much.
Sure.
Okay, thank you. I think there's a question there. Just a second. Yeah.
Oh, okay.
Okay.
Oh, yes. Thank you, Professor Zhang. A very inspiring talk. My background is the energy field. So I am wondering whether your technology also viable in some energy conversion devices like the fuel cells or the electrolyzers, because there are some bubble dynamics inside, like the generation and also the movement or the collapse of the bubbles, which are maybe at the scale of millimeters or the micrometers. So I am wondering whether this technology also viable to that application.
Good question, right? Sensing devices are changing, upgrading constantly as well today, right? We heard about DAS, right? The fiber system, which can continuously monitor things. We have small sensor made from MEMS, very cheap, can monitor machine operating. So if you have any machine, anything, you can install small sensor. Instead of the human inspecting, you use a sensor to sense, is it operating normally or not, right? By AI, you can train what is normal, what is anomaly. So a lot of area you could do. Right now, we're just demonstrating where it could go, but the demand should be huge, like you mentioned. Right now, in the energy sector, we work with the Shell in Holland. We monitor their gas field. Their gas field production could cause induced earthquake and so on. And they have a tremendous lawsuit for the Huntington, the gas field, even 3.2 earthquake causing the building collapse, so on. So we're helping them to monitor that. And we're working on a project in Saudi monitoring the production field. See the traffic, see where any activities. Once you are able to monitor the whole oil field, you can see, oh, it's a human, it's a truck, so on, 24 hours. If any anomaly, then issue is warning automatically. So bottom line, information is very valuable. If you can collect, you can process.
Okay, thank you, Professor Xia.
Okay, this Yongxia from, actually I'm doing bridge engineering, also bridge monitoring for many years. Usually we use vibration, for example, use the accelerometer similar to your sensor to measure the vibration. But we never use sound. Actually, I think you combine actually also sound and the vibration.
Velocity and velocity. Displacement, pressure from sound, right? Velocity from vibration. Acceleration is from vibration too.
Okay. We will learn more. Actually, one question is, for example, for bridge, you show the bridge monitoring, wave motion, for example. One question is, we usually learn to use AI from one bridge, and then for another bridge, we need to learn again. So, or may have to use transfer learning, whatever other AI. So, what's your opinion?
Okay.
Do you do this similarly?
Right. We don't need to do that transfer in our project. We're monitoring velocity. Velocity the frequency can be very low. Acceleration frequency higher, right? It's typically about 10 hertz, 12.5 really. But we're monitoring 0.1 hertz, really low frequency of the bridge. Nothing can simulate that except the bridge itself. And we're using geophysics method to calculate attributes. So observe the attribute, using AI to detect attribute changes, not for calculation, for pattern recognition. So regarding different bridges, as long as the pattern changes, and then our AI will issue warning. We have 4 different level of warning. In that way, it can be generalized to different bridge.
Okay, thank you very much. Maybe later I can contact you with more details.
We should talk.
Sure.
Okay, thank you. So other questions?
Students?
So I have some students here. You remember what I told you. Geophysics is so important. If you can do geophysics, you can do everything. So now you believe me, right? There's a geophysics. In college, his major in geophysics, mine is space physics. Even though we all work, for physics, but the solid background in geophysics can play a big role in your life. Okay, so for the students, do you have any questions? So anything you can ask. For me, I do have a question for you. You are still a human being, right?
Yeah.
You have 24 hours a day, 365 days per year. So how can you do so many things?
Oh, okay.
I count myself as a very productive, scientist, but how could you do so many things? Can you share with, especially with our, young generation here?
I think one of the benefits to study in a prestigious school like USTC or MIT and so on, I witnessed how distinguished professor students, how they do their own things. I learned that in that process, I found that they pick up their priorities, right? As you are moving along, you found that you got to reject a lot of things. You got to choose and, and play. You can't do everything, you have. That's one thing. The other thing is today, based on whatever you do yourself, is very limited. You got to create your own team, one way or the other. Create a team, and then you work with a team to do things. And find out your role, making your role very unique. For example, you mentioned I'm a geophysicist, how I work on biomedical. I found in my biomedical team, we got people from chemistry, biology, medical science, many fields. They don't listen to each other. When we argue, the chemistry people will argue chemistry is so important, right? This is that. And medical people say, no way, how can you inject that into human? They don't listen to each other. They tend to argue with each other. And me, as a geophysicist, knowing nothing, sitting in between, I just listen to everyone. I read everyone's paper. I discuss with everyone. And then I come up with a solution, and they really accept me. So I found, they need someone like me. So I play that role. I can't do chemistry as good as they are, but I can judge as a product which needs contribution from multiple fields, what we should do.
But still not easy. So can you share some recipe? How can you maintain a high level of energy? Right?
Okay.
It must be very.
Yeah, I think if you do things you like, you enjoy, you're really excited, that really, you're driven to do that automatically. Yeah, I like to get up early every morning, 6 a.m., running a few kilometers, and then I have my day. Imagine I'm just so excited. I have this and that. Everything is the thing I want to do. It's not like I have to do. So I'm so just involved. That's one thing. And then the other thing, I think also value driven, right? When you realize you come to your state of career, you can contribute, make a value to the society. You can, whatever you do can influence people's life, and you're very excited, right? So in US, they measure the performance of National Academy member. They say, because of your work or product or publication, how many people's life quality have been changed, have been upgraded? And we're constantly look at that issue, right? So we have so many role models down there doing that. That's how we follow. We're not the first one doing things, multiple tasks for, because of that. We see, oh, wow, so amazing, coming whole life down today. It's not time to get retired. Actually, it's a time to be more excited. You can put all your knowledge, your experience together, do something, changing people's life quality. That's really exciting.
Okay, thank you. Yeah, I completely agree with you. If you want to be successful, you have to like what you are doing, right? So passion is so important. You have the passion of doing the things you like. So while we can give more time for audience to think about your questions, let's start with some questions we already collected. Yeah, I do have a list of questions here. The first one is how to, mostly related to the so-called AI. So how to develop a matching physical model? I don't know if there's any specific reference here. A matching physical model. I'm sure that's probably talking about the AI, the model.
Not quite sure exactly what it refers to, but I guess sound and vibration AI different from image AI. Image, you look at a human, 3 years old can tell, oh, this is mom, this is daddy, so on. But from a sound record, we're just looking at the signal here. Even an expert can interpret without physical model, without algorithm to decode, right? It's an encoding, decoding process. So it requires advanced physics, advanced mathematics, computer science, so on. That's where we have a role to play. And we found that we can't just bring AI expert helping us solve this problem. No way. We have to do it ourselves. So our past experience is such, well, we got to train our student, our fellow to study physics first. And then we're able to do establish a physical-based model to solve AI issue. Yeah, I'm not sure the matching model is talking about, but this is a physics-based model.
Yeah, I think for the second question, you already answered mostly. So how can I improve my research efficiency? So what routine do you follow for each research project?
Okay, that's a good question I answered, but also I should have something else to share with the people, with the audience. I found it very interesting. We have different type scholars, researchers, and some are very focused on their own work, not carrying other people. Others constantly watch and learn and then do things. At MIT or Stanford, if I want to schedule appointment with someone, a professor, to meet, it's pretty hard actually. They are all busy. But I found that there's a trick. You can meet with them. If the department invites a speaker coming to give a talk, those guys grab a pizza and just squeeze into the door. They gotta be there and listen, because from presentation you can tell what's the most recent progress from that group or individual research. You gotta be constantly sensitive what the whole world is doing instead of just doing your thing. So doing the right thing very important. The secret in science, we know there's only number one. There's no number two, right? If someone already doing that or doing better than you, you got to think about way either beat that guy or do something else. How? You have to be sensitive to the academic world, the researchers around. So I think doing the right thing, you need to communicate. You need to be sensitive, watch, and any opportunity, conference, any presentation, go there to steal some ideas, right? So that's a point I want to make, doing the right things. And then the other thing I already mentioned, do important things. Just you have to reject things to do at some point. You can't do everything assigned to you. You have to pick and choose most high priority things.
Okay, thank you. The next one is what could be the applications in public health dimensions?
Probably means
The
machine
current-
listening.
The current technology?
Machine learning. In medical imaging is all developed. I mean, medical imaging, vibrating ultrasound technology, X-ray technology, imaging technology is very advanced. FDA approves so far over 600 medical devices using AI. A lot involved with the sound, vibration, those things. So already there. Unfortunately, they banned export of this device to China, and so on. So we don't see them. You have to be in the U.S. and knowing the progress. But going to a conference like RSNA in Chicago, larger medical imaging, you can hear a lot of, recent development. So a good question, but hard to answer. I encourage people, trying to attend a conference as much as you can, especially today, when the communication is very limited. You got to know what's going on in the world.
Okay, thank you. So I want to pause for the online questions and then come back for the audience here. Do you have any further, question? Yeah, here.
Okay, thank you, Professor. I'm curious about the data format of the machine learning model, machine listening models. I mean, for the language models, there are tests and kind of image models, the image and videos. I know some format like MP4 and MP3 and other formats. So concerning the machine listening, about the examples you provide in the presentation, what are the data formats of the input and what's the format of the output of those models?
Oh, okay. Each field has their own standard. Like in medical imaging, they call the DICOM, right? DICOM, DICOM, defined around the year 2000. That was the image, sound image data format. Globally, they creating a standard. So every device come out, you got to say DICOM Vision 8.3 compatible or 8.1 compatible. So they upgrade every year, so you have to follow that. In seismic industry, they have a SIG-Y format or SEED called SEED format. So they upgrade that at the same time as annually. You need to create data, and the device have to create that format for you. So they'll have their own standard you got to follow. Yeah.
Okay. Thank you.
Okay, thank you. So other.
Thank you, Professor Chen, for facilitating, and thank you, Professor Zhang, for your detailed sharing. That's really inspiring. So you mentioned many applications of machine learning in various geophysical fields, and which gave me a lot of inspiration. But actually, I'm from a textile background. So actually, I have an idea on mind that, like, for example, for elderly people, they're living at home, if they accidentally fall or get injured or they cannot move. So maybe they can only make some subtle sounds. So I was wondering, like, could the machine learning models be trained on the weak signal detection, like, which is similar to the one that you mentioned in your sharing? And I would like to ask, like, what do you think of the viability and also the technical feasibility of this kind of application? And also, there's an extra question, like, besides the seismology and also the geophysical exploration, do you think that machine learning, like machine listening, has more promising cross-field application scenarios, especially in wearable or smart textiles related directions? Thank you very much.
Oh, thank you. Right, a good question. Right now we already extend from traditional geophysics to urban environments, right? Traditionally, our geophysics doesn't come to city. We're in the field, oil gas field, all large area to monitor earthquake tectonics. But now we're in the city, so this is a major thing. Which drives me very exciting every day. My goal is together with my team, we want to create a new field, hopefully creating job for over 1 million people. And this is a new task. It is a platform technology. It's not a one specific application. Platform technology means you can apply that to many vertical market. I showed in the transportation market, I showed in infrastructure monitoring, natural hazard, right? But you can even go further beyond. My students work on a project monitoring seniors in the house. Single senior, usually you don't know the activity, worry, right? You use a camera, they don't like that. So if you have a sensor in the house, you can monitor every day the walking tempo and computing the health status, so on. If he or she falls, you can send a message automatically to the relative, so on. So we have that, and also our student doing things for robots, install the sensor in the air. Later they found that the air is not good. Put on the shoulder, better, the separation. And then they put it in the feet, seismic sensor. So a platform technology, it can be go on and on to different applications. See and listen are the two fundamental, capabilities like humans that, AI has to simulate one way or the other. Yeah.
Okay, thank you. So we have time for other questions.
Thanks for Professor Zhang. I do have another question because this is a very precious chance to communicate with you. So my question is also related to the image. So if we use like velocity change, DV or way to detect some abnormals like sinkhole or collapse, so how to reduce the uncertainty in this part? I mean, why do we know it caused by the single or collapse instead of the difference of rock properties of the fluid or something like this. So for my own research, I often I'm confused in this part too.
Yeah, I
That's
see.
my question.
Right. That's why this type of engineering effort demands collaboration between academia and industry. We need a lot of detailed studies. For example, the one you mentioned, you monitor, you realize dV over V changes. What is that? You know, is it collapse? Is that water saturation? Is it something else? So seismic industry has done a lot more for using different method to confirm, to just from single seismic technology. How can you justify that's the oil water interface, right? They do a lot of different type of research. And same thing for us. Not only dV over V, you can monitor the reflectivity. You can extract from ambient noise. You can calculate the power spectral to understand the vibration on different attribute, using multiple attribute to judge. For example, if a collapse, it cannot be recovered. It will be permanent change. Right? If the velocity saturation is a water saturation, then causing something to gradually recover, and maybe or something. So multiple attributes you got to look at. That's how oil gas industry work on that. Instead of one parameter, they do multiple attributes. Yeah.
Okay, thank you. We probably have time for only one last question. Professor Xia?
Yeah, again, yeah, many people now talk about the AI. Yeah. Actually, if you know AI, then somebody said we don't need to learn the math or mechanics. Actually, it's I don't agree, of course, but it can lower the bar, yeah, because it's more easier to get the result or solutions. Yeah. So what you can estimate your viewpoint in the near future in the education, particularly? Yeah.
It's a very good question. January, February this year, I was in the U.S. Meeting with many scholars in the U.S., university presidents, and so on. They were frustrated with the situation. You know, computer science, double E, are supposed to be hot, right? Like at MIT, double E computer, the first year, they attract 85% of undergraduate students. And then later they go to different departments. But not now. One message I learned from a panel section discussion, AMD, you know, and so on, the company CTO, they talk about they only need about 5% of, you know, computer people they have today. So that's a huge change. Many companies began to hire people with the experience only, you know, longer than 10 years. If less than 10 years, they don't hire. Especially with the open cloud appears, right? Agent, the real agent. So last month, we invite Kevin Kelly, AI, you know, expert from Silicon Valley. He came to China. He talked about we can't predict the job 2 years later in AI. We don't know. 2 years later, the job is not invented today. We don't know what's like. And then the typical situation is one guy sit here with probably a dozen agents, operating a dozen agents. There's just like a dozen computer terminals. You don't need a lot of people, but you do need a sales force. You do it most students from humanity, probably. And they found, and some company began to hire people from humanity because they found that those people have creative ideas. And then they tell the tools, they tell cloud, they tell ChatGPT, then especially open cloud, they can do whatever you want to do. So the world is changing. It's a huge challenge to university, regardless you realize or not. So what about computer guys, you know, programming guys? We don't need them. So they first killed job market for that programming. And then many areas, right? So APP, they no longer need APP because an agent can do a lot. A2A market, Kevin Kelly said A2A market becomes a reality. Agent, pay agent using their money, right? And then the next day in China, news release, or agent creates a job and selling the job to human. So I can't do this. I issue 3,000 yuan. Whoever can do that, I give you 3,000. It's so A to human, the market appears huge challenge. What happens? So we don't know. No one is on the frontier who can understand everything, but definitely changing the world. Definitely changing. We have to be sensitive, constantly watching. Yeah. And one thing it doesn't change. You got to learn physics, chemistry, biology, the fundamental science. That AI cannot. You have to do that yourself, right? Yeah, you have to teach AI agent to tell them. It takes 10, 15 years to train a professional guys in certain field. But for AI expert, you probably take a year. Right now, shorten that with all the AI large models. You can train someone to become a expert in 2 months, right? And then he or she learn how to manage open clouds, the lobster, the so-called in China we call it lobster, and so on. So it's just changing. Yeah.
Okay, thank you. Unfortunately, we have to come to the close of the QA section. Yeah, let's thank Professor Zhang again for the inspiring presentation.
Thank you.
So to express our appreciation to Professor Zhang, prepare a special plaque for you. So with your name and the title of your lecture. Thank you so much. It was really great to have you here. So now the lecture is adjourned. Thank you.